This lecture is part one of a lecture on section 4.2 from Math 311, a course in linear algebra at Western Illinois University. So we are finally coming to the topic of determinants, which is what one of the more familiar topics. Every linear algebra course has them. We've sort of postponed this discussion until now because we really want to focus on not so much how determinants are calculated, but what they're useful for. And we've already defined a determinant for a 2 by 2 matrix, and we actually use that to find the inverse of a 2 by 2 matrix, and we found that the inverse exists only if the determinant of that matrix is not 0. And now what we're going to do is we're going to generalize this topic of determinants to any square matrix, and it'll turn out that that matrix will be invertible if and only if that determinant is not 0. And this kind of reflects one of the wonderful and yet mysterious aspects of mathematics, where you prove to find a solution of a problem, you prove that a solution exists without actually finding a solution. So that's what determinants do. They determine if a matrix is invertible or not without necessarily producing the inverse. So we're going to go through this, and we're going to give several definitions of determinants depending on what the size of the matrix is. So we're only going to be working with square matrices, and we say the determinant of a square matrix A, which is denoted either by det or it looks like the absolute value sign of A, is defined as follows. A 1 by 1 matrix consists of one entry, so that entry is the determinant. We already know that 2 by 2 matrices, the determinant of the matrix A, B, C, D is AD minus BC. And now what we're going to do is we're going to actually define the determinant of larger matrices in terms of determinants of smaller matrices. In particular, if n is a matrix, if n is greater than or equal to 3, we define the determinant of A to be the sum of all expressions of this form of we're summing -1 to the 1 plus j times the 1j entry of A times the determinant of capital A1j, where capital Aij is just A with the ith row and the jth column removed, and as a result it's an n minus 1 by n minus 1 matrix. And of course this is assuming if we know how to find the determinant of an n minus 1 by n minus 1 matrix, we should be able to compute this. This should make sense, and then we just add all of these up. Okay, so this seems like a very complicated definition, and it's actually one of the nicer definitions of determinant. There are other ways to define and calculate the determinants, but this relies on knowing how to compute determinants of smaller matrices. So let's look at how to compute the determinant of a 3 by 3 matrix. And basically what we do is we're going to go across the first row here and cross out this row and one of the columns, and then take the determinant of what's left. So when we take the A, we cross out this column, this row, and we get EFHI, which is right here. We cross out B, we get for B we take the first row, second column, and we get DFGI, which is this determinant. And then for C, we cross out the top row, third column, and we get DEGH, which is this. And the minus sign here comes from the fact that B is in the first row, second column. So 1 plus 2 is 3, which is odd. So -1 to the third power is E. Whereas here it was this was the 1, 1 entry, and there this was a 1, 3 entry. And you add those, make the indices, and you get even. So that's why you have this. And then you can, if you wanted to, you could multiply this out. This would be EI minus FH minus B times DI minus GF plus C DH minus EG. But no one memorizes this really, okay? I know that there are some ways, some people did it in high school where they might have added a couple columns here and do stuff with diagonals, but really this is the most efficient way to memorize this. So you really don't want to memorize any formula, you want to memorize the process. And you can do that by expanding out across the first row and then computing all these determinants. The one term that we have is this idea of a cofactor, and that's just the determinant of the ij cofactor of A is just the determinant of the matrix you get when you delete the ith row in jth column times -1 to the I plus j. So really what we have in our here is with this is really basically just the sum of A1j, C1j, okay, where j goes to 1 to n in this case. Now the okay, and then we could we could generalize this to we can take the determinant of any matrix, like a 4x4 matrix. We would just basically do this, and we just have to compute about 4 3x3 determinants, and of course that each 3x3 determinant is going to take a while, and of course lots of opportunities to make arithmetic errors. So because we have computers and calculators that will actually compute these determinants for us, we're not going to focus too much on the computations. We're going to focus on the properties and what these properties, what information these properties tell us. But just want to be aware of a few things about computing. The nice thing about this, about determinants, is that you don't necessarily have to just expand this using the first row. Turns out you can use any row or any column. Just go across and just for example, you could take the second row here and then cross out this column and this row, and then find the determinant for the resulting matrix, and then go do the same with this entry, and then do the same with this entry. You just have to realize that here, because D is in the second row, first column, you have a minus here, and then a plus here, and then a minus here. But to formalize this, we have the Laplace expansion theorem, which says that as long as n is greater than or equal to 2, the determinant of A can be computed this way. It's just Aij, the sum of Aij times the ij cofactor as j goes from 1 to n. This holds for any I. So this part basically says that you don't have to use the first row. You can pick any row you want to expand over this. And then this next one says that this will hold for any j. If you let I run from 1 to n and fix j, then this sum will be the determinant for any j. So this basically says you can expand, expand along any row or any column. Okay, and that's the Laplace expansion theorem. Now, this is, unfortunately, the proof of this is very, very difficult, and I'm not going to make you to memorize, to study the proof or memorize it. It is in at the end of section 4.2, and it's a little lengthy. But the nice thing about this is going to help us prove so many other things in this lecture. So I want to, before going on to the theory, I want to just do a few examples here. And here we'll start with this 3x3 matrix. So if we want to, let's say we want to find the determinant of this matrix by expanding along the first row, like the original definition said. Okay, so this would be 1 times the matrix 3, 5, -4, 2. And then we have minus 2 times the matrix -1, 5, 6, 2. And then we have plus 3 times this matrix -1, 3, 6, 4. 6, negative 4, rather. Okay, and you can check the calculations, the arithmetic. This is 3 times 2 minus negative, so this would be 6 minus negative 20. This would be 26. This would be 26. This would be negative 2 minus 30, so this would be negative 32, and this would be 4 minus 18. This is negative 14. And you can check that this is equal to 48. Okay. Now let's see what happens if we expand it around the second row. All right. So now we start with this. This is in the the second column, second row, first column. So 2 plus 1, that's 3, that's odd. So this is going to be negative 1 times, we cross out this row, this column, we get 2, 3, negative 4, 2. Okay. Now this is the 2, 2 position, so that's plus 3 times the matrix 1, 3, 2, 1, 3, 6, 2. And then we have minus 5 times the determinant of 1, 2, 6, negative 4. Okay. If my arithmetic is correct, this is 16. This is negative 16. And this is negative 16 as well. So this will be 48. So you should get the answer. And we can do columns as well if we wanted to expand around the third column. That is this one. We cross out this for 3 is in the 1, 3 position. So 1 plus 3 is 4. So we start out positive. So it's 3. And then we have negative 1, 3, 6, 4. I'm sorry, negative 1, 3, 6, negative 4. Okay. And then in the 5, we cross out this row, this column, and we get 1, 2, 6, negative 4. So this is a minus 5. 1, 2, 6, negative 4. And then finally we have plus 2. We got 1, 2, negative 1, 3. Okay, and if we compute this is going to be negative 14, this is negative 16, and this is 5. Okay, if my arithmetic is right, this is 48. Okay, so if you want to check, you can pick some other rows or columns and expand it, but you should get the same answer. Okay. Just to do a 4 by 4 matrix. Now, the fact that we have some flexibility in checking our column or row, that's helpful, because the more zeros we can see, the easier things will be. And because in the third column here we have 3 zeros, that's probably the way we want to go, right? Because if we expand along the third column, well, what we'll have is 0 times something, plus 2 times something, or minus 2 times something, plus 0 times something, minus 0 times something, right? And we don't really have to find all these other cofactors. We just have to find this part right here. So this is the determinant of A is going to be negative 2 times, okay, so we cross out the third column and the second row, and we get 2, negative 3, 1. And then over here we have, we're crossing out this row, so we have 1, negative 1, 3. Okay, and then finally we have 3, 6, and 0. All right. Okay, now here we also have a very nice situation where we have a 0 here, so that will help. So we can probably just go ahead and expand along this column right here. we want. So this is going to be -2, and then this will be 1 times the matrix 1, -1, 3, 6. Okay, and then we have -3 times 2, -3, and 3, 6. Okay, so this will be -2, and this we can see that, I'll just say that this is going to be 6 minus 3, that's plus 9, and this is going to be 21, that's 12, that's 12 minus -9 is 21, and then when you compute everything, this turns out to be 108. Okay. And again, one thing, if you're a little confused, why all these pluses and minuses, one way to think about this is if this is your matrix, it's helpful to see that the pluses and minuses alternate as you move along any row or any column. Okay, so if you just think about where you're starting, you start with a plus or a minus, and then you alternate. So this is how we compute determinants. Now, again, you should be able to compute this by hand. Although, I'm probably not going to ask you to compute like the determinant of a 5 by 5 matrix, or even a very complicated 4 by 4 matrix. Okay, unless there are a lot of zeros in it. We have computers and we have calculators that will compute determinants if they're relatively small. The purpose of this section really is just to see how we can use determinants to find out about the invertibility of matrices and a lot more. So that's what we're going to be doing in the next video.